Hello, I'm Noam, and this is Will, and we're Group 8. The project we've been working on is called COVID-19 Risk Model on Microscopic Data in the European Population. First, I'll give an introduction into COVID-19 risk models. In general, risk models are used to understand which regions or populations are most susceptible to certain diseases. And for most COVID-19 risk models, they are microscopic, meaning that they look at data from individuals, often clinical or health data, such as vital measurements or presented symptoms. So these models neglect macroscopic data, which is population level data or environmental data or socioeconomic data that affects the population as a whole. So the goal of this project is to develop a simple and reliable risk model of COVID-19 based on a macroscopic view with the aid of machine learning. And our proposed approach is to compare various implementations trained with population data with and without environmental data.
For our proposed approach, we took our methods and divided them into three major steps. The first is data preprocessing, where we acquired the data and then we cleaned it up and divided them into training and testing sets. Then we looked into applying this data to our risk models, where we performed analysis on three different classes of models, where we had linear models, more complex models, and an ensemble training model. And lastly, we looked at hyperparameter optimization for our more complex regression models. For our data preprocessing step, we acquired a data set that's publicly available, compiled by Omrani et al. In their study on COVID-19 data in Europe, where they gathered population and environmental data by NUTS 3 regions in Europe, which are municipal and local regions. And then looking at this data, we filtered which features we would be able to use and categorize them into population data and environmental data, where some examples of population data features are age distribution and population density, whereas for environmental data, we had average temperature and average air pollution. The target for our models was the COVID-19 mortality rate. So we included that column as well. And we first divided our data into a training and testing split. And then we formulated a population data only data set and a population and environmental data set. The three classes of models that we used were linear models, where we had a linear or ridge regression model, which are simple with no nonlinearity. Then we looked at more complex models, such as the multi-layer perceptron or support vector machine regression models, which are more complex and can have nonlinearity with the appropriate activation functions and kernels. And then finally, we looked at an ensemble learning method with the random forest regression model, which are the most complex and can accommodate nonlinearity pretty well. And then finally, moving on to our hyperparameter optimization, we conducted a tenfold cross-validation for each of the models that we could have hyperparameter optimization with, which are not the linear class of models, but for the MLP and SVM regression models, we looked at different hidden layer sizes, and then the error and curvature hyperparameters. And lastly, for the random forest regression model, we looked at various hyperparameters on the tree itself. Then moving on to how we did this in code. So first, for each of our models, we standardize and put all of our processes into Jupyter notebooks, where for each model, it will load the data, train on it, and also display the coefficient determination results. And as you can see here, if you just run the entire notebook, it will do all of those steps at the same time. And then in addition, we actually uploaded all of our code onto a public GitHub repository so that anybody can access it. The data is available in our data folder, which contains the raw data as well as all the preprocessed and then training test splits that we used. We have a data preprocessing script, as well as the notebooks for each of the models, as we saw before. And as an example, here's our random forest regression model notebook. and you can see all of our results right here. Here we are.
So now that we've seen how our code runs, I'll get into our results. So to analyze and compare training accuracy for each implementation, we calculated its coefficient of determination for every parameter combination in a grid search for MLP, random forest, and SVM. So these are the heat maps that resulted from these grid searches. And you can see here for MLP and SVM, for the hyperparameter search that we conducted, we didn't get a very good coefficient of determination for training results. So it's relatively low. And then looking at the random forest, it's still relatively low, but it's higher in comparison to the MLP and SVM models. And this is just trained with population data only. So when we look at population with environmental features as well, these are results for training. And again, MLP and SVM did not improve that much, although they did improve. And random forest jumped up to about 0.56. So this is the highest among these three models. And again, this is just for the training data. So when we go on and take these trained models along with the trained models of linear regression and ridge regression, we can compare the final population versus population and environment coefficient of determination for each implementation when we run our models with our test set. So first, looking at our models just trained with population data, you can see again that the coefficients are relatively low. Random forest is the highest with 0.113, but then models like MLP and linear regression are quite low in comparison. And then when we look at population and environment data, so when we add our environmental features to population features, for every single implementation, the coefficient of determination increases. Most notably when looking at linear regression and ridge regression, it goes up to about 0.2. And we attribute this to the linear models being simple enough that when we run our data, it's a decent, has decent predictive power. While when we look at our MLP and SVM models, because they're more complex, maybe we need to do more hyperparameter tuning and do a wider search. They just require possibly more attention and fine tuning. Then finally, for the random forest, it's the highest overall for both population-only data and population and environment data, with a final test result coefficient of determination of 0.281. And we think that this is due to random forest using ensemble methods, which are known to improve the accuracy of nonlinear models. So just to conclude sort of the outcomes and significance for our project, what we did is for each model, we included the inclusion of environmental factors improves the predictive power of the models compared to when you just train the models with population data only. And then again, the MLP and SVM models performed the worst among the five. And we think this reflects their complexity and the need for more optimization. The random forest model, which, as I said, is an ensemble model, it has the best performance, and it also has the lower training time, especially in comparison to MLP, which takes much longer. So this agrees with the results previously published by Gao et al., and it also has motivation to keep using random forest since we do want a simple model as well. And so again, the goal of our project was to find a more accurate risk model in order to allow for beneficial policy decisions and reduce mortality rate in the future if we are able to implement these models for actual real life use. So future work based on our project first would be to implement the random forest regression model with more hyperparameter fine tuning and even more data. As we saw that when you add your environmental factors, we do get an increase in predictive power, but we want to go even further in doing more fine tuning to get that to a number that's more predictive. We also would apply our models to more or other target outcomes. So instead of just looking at mortality rate, we could also look at infection rate or recovery rate to see if our models are applicable for other bits of information. And finally, we would also be interested in applying our models to other diseases, such as influenza, to see if these types of models can be predictive for diseases beyond COVID-19 and have an even broader impact. With that, here are our references for this project. Thank you.